Today we are going to look at the very important topic of verifying trigonometric identities. This is an important step in being able to work with identities, primarily because where do we get identities from? As we saw in our last discussion, one of the ways we can get identities is by starting with facts we know about trigonometric relationships and building on those to come up with new relationships. Another way is to simply take an expression and work to determine whether or not that is an identity. So the big question for today is, how do we know when something is an identity? Okay. Identities are very powerful. We will see that they will allow us to do many things to greatly simplify our work later on. But we can only make use of the identities that we know. So if we don't know very many identities, we're limited in what we can do. If we know many identities, then we're able to get much more accomplished. So I want to start today by writing out an expression here and trying to understand whether or not this expression is or is not an identity. And we're going to talk a little bit about different ways of determining this. And we'll find that there's only really one very useful way of doing this. All other ways are rather limited. So my question for us today is to determine, is this an identity? Now recall, an identity is an expression that's true for any value of the variable. So that means any angle we choose, do we get the same thing on the left-hand side and the right-hand side? Now think about how you might approach a problem like this. How could we show that this is an identity or is not an identity, depending on what the actual results are? How could we do this? Well, one way to go through and do this problem may be to test points. Is that a valid way of determining whether or not this object is an identity? Suppose we decide, for example, to test the point x equals pi over 4. So we have 45 degrees or pi over 4 radians. We're going to evaluate this trig function at this particular angle. Okay, so what does this look like then? This looks like the sine of pi over 4 divided by the cosecant of pi over 4 plus the cosine of pi over 4 divided by the secant of pi over 4. And we want to know, does this equal the cosecant squared of pi over 4 minus the cotangent squared of pi over 4? So here's our question. Does the left-hand side equal the right-hand side in this case? So now we can go through and recall what we know about these various trig functions and evaluate this expression at different places. The sine of pi over 4 is the square root of 2 over 2. The cosecant of pi over 4 is 2 over the square root of 2. The cosine of pi over 4 is also the square root of 2 over 2, and the secant of pi over 4 is 2 over the square root of 2. The cosecant of pi over 4 is 2 over the square root of 2, and that is squared. And the cotangent of pi over 4 is 1, and that is also squared. So we have to verify that the left-hand side and the right-hand sides of these two expressions are equal. Well, the square root of 2 over 2 divided by 2 over the square root of 2 ends up being the square root of 2 squared over 2 squared. And that's true for both of these expressions here. The square root of 2 squared over 2 squared. And here we end up with 4 over 2 minus 1. So if we continue our evaluation of this expression, the square root of 2 squared is 2. 2 squared is 4. So we end up with 2 fourths plus 2 fourths. And over here we end up with 2 minus, and over here we end up with 2 minus 1. If you work this out now, we have 1/2 plus 1/2 on the left-hand side, and we have 2 minus 1 equals 1 on the right-hand side. So sure enough, we end up with the fact that 1 equals 1. But are we really any closer to answering the question, was our original expression an identity? Recall that for something to be an identity, we have to be able to know for a fact that it is true at every single value of x. Now we picked one particular x value. We picked an x value that we knew the exact values of these trig ratios for. And so we certainly have not proven that it is not an identity, but only picking one point is not sufficient. This is not a good way of testing whether something is an identity or not. Okay? It's very tedious and long, and we would never ever finish it. So this is a poor method. It's a poor method because we can never test every single point, and in not testing every single point, we leave ourselves open to the possibility that at some point that we didn't test, this ends up not being equal on the left and the right-hand sides. If we were to test 100 or 1,000 points, we'd probably be very confident that the left and the right-hand sides here are equal, but again, that's not considered a verification mathematically. Another way we might choose to do this would be to graph. Okay. Are the graphs on the left-hand side and right-hand side equal? Would that be enough to prove that we had an identity? Well, it just so happens that we can take a look at these graphs here and discuss whether we think this is a good method or not. So the left-hand side I've had to rewrite strictly in terms of sines and cosines using some of the identities we learned before. And here you can see the function. And the function happens to be a perfectly straight line. That's interesting and might help us later on in solving this problem. But you can see that this is a horizontal line. It's actually the horizontal line f of x equals 1. On the right-hand side, if we graph that as well, sure enough, you can see that that is also a horizontal line, at least between minus 4 pi and positive 4 pi. So now we have done something here. We have graphed the left-hand and the right-hand sides of these equations, and we have seen that in this region they are equal. Okay? Is that a sufficient proof now that we have an identity? In other words, is a graphical method going to be sufficient? And unfortunately, in this class, for you guys, I'm going to say that this is a poor method. This is a poor method unless we can see the entire domain. It's always possible, and especially with trig functions, you have to be very careful of this. It is always possible that way out at some other place, these two functions do start to do different things. Now, in this case, it's not. In this case, the left and the right-hand sides are identities, but being able to look at graphs is not necessarily a sufficient way of doing this. So, we really only have basically one further way of checking that this is an identity. Okay? This is an identity if the left and the right-hand sides are actually the same thing. So this is an identity if the left-hand side and the right-hand side can be written in the same way. In other words, if I can make the left-hand side and the right-hand sides look exactly the same, then we have ourselves an identity. If they look the same, then they must be the same. So this is interesting because what it means is that we're going to show that this is an identity by using identities. And let's see how that works. So we'll start here with our original expression. We had the sine of A over the cosecant of A plus the cosine of A over the secant of A, and we want to show that that is equal to the cosecant squared of A minus the cotangent squared of A. So what we're going to do here is we're going to modify, we're going to rewrite the left-hand side, we're going to rewrite the right-hand side, and we're going to show that these two things really are the same thing. If we can show that they both are really the same thing, then we're able to prove that, of course, it's an identity. The left and the right-hand sides are really the same thing. So there are a couple of rules that we have to follow here as we go through and do these problems. And the first thing is we're not allowed to switch sides. We're not allowed to move things from one side to another. Clearly, if we're trying to show that the left-hand side and the right-hand side are the same object, we can't be moving things around. We can't do the same thing to both sides. We can't do any of those algebra tricks. What we're going to be doing instead is rewriting things in the way that we know how. So I'm going to start by using my reciprocal identities to rewrite the cosecant down here as 1 over the sine. And I'm going to use my reciprocal identity here to rewrite secant of A as 1 over the cosine of A. If we get this far, now we can see a step we can take. We can actually, since we're dividing by a fraction, I can rewrite this as the sine of A times the reciprocal of 1 over the sine of A, which is just the sine of A. And the same thing here for cosine. I can rewrite this as the cosine of A times the cosine of A. And if we do this, sine of A times sine of A will give us the sine squared of A. Cosine of A times cosine of A will give us cosine squared of A. And of course, we know from the Pythagorean identity, which you should already be starting to have memorized, that sine squared of A plus cosine squared of A is equal to 1. So then we can ask ourselves, what are some other ways of expressing the number 1? And if we start with the Pythagorean identity for sine and cosine, we see cosine squared A plus sine squared A is equal to 1. And here I'm going to make use of a very important trick. This is something that you build with time, this instinct of how to approach problems. One of the things I can say here is that the right-hand side, with its cosecant squared minus cotangent squared, those squared trig functions automatically make me think of the Pythagorean identity. So I'm going to try and rewrite my Pythagorean identity in terms of cosecant and cotangent. To do that, I'm going to divide everything by sine squared. When I do this, I end up with cotangent squared of A plus 1 is equal to the cosecant squared of A, or 1 is equal to the cosecant squared of A minus the cotangent squared of A. That means that the 1 that we had on the left-hand side can be written as the cosecant squared of A minus the cotangent squared of A. But that is simply what the left-hand, or the right-hand side rather, of our original expression was. And therefore, as we have gone through this problem, we have managed to change the left-hand side of our expression here. We've managed to change the left-hand side of our expression so that it looks identical to the right-hand expression. Here you can see that right down here, that we end up with the same expression on the left and the right hand side, and we were able to get that. We were able to get that here from the original expression. So what we really ended up doing was modifying a bunch of material to come up with that.